I want to talk about the next topic that we're going to be discussing in Physics 221, and that is the electric field. And what is it? And I want to tie it in, the way I want to introduce it to you is I want to tie it into what we've been doing. So far, the last couple of weeks, we've been talking about having two charges, or more, maybe three charges, and looking at the force that each of those charges experiences as a result of being near the other charge. That is Coulomb's law, and we have an equation, we can calculate it, we can come up with directions of that force and all that. Now, what if I just had a single charge sitting in space, somewhere in space? And I want to know, well, what would the force on another charge be if there were another charge somewhere? But let's say there isn't. So we can imagine, okay, what if there were a charge here or here or here or here or here or anywhere? Could I figure out what the force on that charge would be? And the answer is yes, I can. And for a single charge, that force would be equal to, of course, if I knew the size of that of any of these charges, I could apply Coulomb's law to find what force it would have if it were there. But in this case, so if, for instance, this one here, if I knew how big it was, I could determine what force it had. But let's say I just want to come up with like a generic, if there were a charge anywhere in space, what force would it experience? That is what the electric field is. You could say, well, if I knew the electric field, which I'll call E, it's a vector, and I multiplied it times some charge that's in space, like this charge here. So basically what I'm going to say is that any charge creates an electric field. And any other charge will experience a force as a result of being in that electric field. Like this one here. Of course, you could argue this one creates its own electric field. Indeed, it does. But if I'm only interested in the force that this one experiences, then I can just think about, well, what's the electric field that that one creates, and multiply it times the size of this charge here, and that will give me the size of the force that that charge experiences. Okay? So you might be able to imagine now, if I had a single charge in space, I'll go back to this little charge here. Single charge in space. What would the electric field be associated with that charge? Well, I could say, well, it's some I need to know what the distance is. So at some distance away from that charge, d, I'll mark a point x. What would the electric field be here? Notice there's no charge there. There's just a location. How could I find it? How could I find what that electric field strength is? The way I would do it is, if you look at this equation up here, I would take the force and divide it by Q, and that gives me the electric field. Seems kind of relatively easy to do that. So we know how to find the force for a single charge. Caused by two charges. It's equal to KQ1 times Q divided by R squared. That's how big it is. All right, so if I want to find out what the size of the electric field is, the strength of the electric field is equal to, we'll divide this whole thing by Q. It's equal to K times Q1 divided by R squared. It's an even simpler equation than Coulomb's law. You just need to know the distance away from that charge that you're interested in. I guess I should have called this R, not D. Square it, multiply K times the size of that charge, Q1, divide it by the distance from that charge squared, and that gives you the strength of the electric field at any point in space. And then the direction, so this is the strength of the electric field. The direction of the electric field is equal to the direction of the force that a positive charge would have felt. If it were at the point in space. Or it would have experienced, I'll say. If it were at that point in space. So what do I mean by that? Well, let's go back to our original situation here. And let's say that I'm interested in that point right there. Well, if there were a little charge here, a positive charge, it would experience a force to the right, I hat. If it were here, it would experience a force j hat, if it were a positive charge. That is the direction of the electric field. It's always defined to be what direction would a positive charge field experience or feel if it were at that point in space. If it were at this point in space, it would be some combination of I hat and j hat, plus I hat and plus j hat. Okay, that's your introduction to the electric field. The last thing I want to say, see if you can guess the units of the electric field. Remember, go back to the definition. Electric field is equal to the force divided by the size of the charge. So the force is in newtons, size of the charge is in coulombs. This is a unit of the electric field, the Newton per Coulomb. Okay, this is your intro video, and we will keep talking about electric fields pretty much for the rest of the semester. They're pretty fundamental to all sorts of things. All right? And you can liken it also to the gravitational field. It's there. If you put a mass in it, that mass then feels a force. But without a mass, there's no force. There's just the opportunity for a mass to feel a force if it were placed there. You can think of the electric field in the same light, or in the same way, but for charges.